Hello, Zoom people. Cool. Step one. Up, 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 up. Okay, let's go ahead and get started for the day. So today we'll be covering finite state machines. This is the first sort of frequently used outside of dialogue systems, sort of for representing AI behavior in games that we're going to be covering. Before that, typically, as usual, some announcements. Is this desk shorter than usual? Is that even possible? Probably making that up. Announcements, quiz 1, oh wait, hold on. I think I forgot to update that. Quiz 1, in fact, has been fully marked and released to you. That's very funny. Quiz 2 is on Friday. That's certainly true. The quiz 2 topics are going to be all pairs shortest paths, because we didn't actually fully cover it last time. So expect that to be a potential thing that you have to answer questions about. Trees, because we talked about it. Monte Carlo tree search follows from trees. Rule systems, so that was all of Friday's lecture. Finite state machines, which is today's lecture. And you have to be able to have the basic concept of Wednesday's lecture, which is going to be on behavior trees. Okay? As per the usual, on Wednesday, I'll try to leave maybe 10-ish minutes, right towards the end, to be able to say, hey, if you have any questions on any of these topics, you can ask them then. But also feel free to not wait for that. You can also go to the Discord, right, and just post in the quiz discussion and ask any questions that you have, right? As with the last quiz, right, I will not, keep on saying right, I don't know what's up with that. I will not answer fundamental questions about how these things work during the quiz, because they'll probably give away an answer. So if you have a question about how any of these things work, make sure to ask it before the quiz starts Friday. As with the last time, there's no lecture on Friday because there's a quiz on Friday. However, I will be here. Only like 3 people showed up last time, so I don't know how frequently I'll stay showing up here. Maybe I'll just be on the Google Meet or something in case people want me in the future. But I'll at least be here for Friday's lecture because I'll be on campus anyway. Any questions on any of that? Yeah.
For they didn't put out the score, they just put up for the latter half, left after the things I had.
That shouldn't be right. Send me an email. The score should be updated on eClass. If they didn't, then that's a mistake. Anybody else? Okay. I will say a whole bunch of people have already emailed me about quiz 1. I think 4 or 5 students have emailed me about quiz 1, but I've ended up changing scores for 2 of them. So, it's worth reaching out, worth double checking your quiz 1 marks. I'll also note that it's worth remembering things like graphs, A*, and other things that have come up in past lectures. They're just not going to be the focus. The basic distinction here is sort of, I might ask you things that conceptually draw on these things from earlier, but I won't ask you to run an algorithm like A* or something like that on that quiz. That's the distinction here. Okay, and then homework 2, assignment 2 is due tonight, and assignment 3 has been released as of last night. I think I heard some people mentioning about it. And as per the usual, we'll cover it right at the end of this lecture. Okay, so last class we covered, we had a nightmare of technical issues, very fun. But I think we mostly got through rule systems, and we talked about sort of the benefits to rule systems and issues with rule systems. The things that we didn't end up covering were like specialized representations for how you handle rule systems. I just gestured, you might want to use a tree, but we didn't actually get to talk about it in detail. But otherwise we covered everything, which is nice. But we have this problem in game AI, which is that most actions require more than one rule. So if I want to do something in a game, right, I almost definitely need to do more than one rule firing at once. Let's say it's as simple as like, I have a waypoint of going to that door and closing it, right? If I'm in a state right here where I'm idly lecturing and I'm about to go into like, I need to go over there, right? This is more than just an if then. It's more than just saying, if I need to go to the door and close it, then run a star, then move yourself over there, do any path smoothing you need to do, et cetera, et cetera, et cetera. There's like a whole bunch of things that need to happen in sequence for me to do this action that I'm doing right now, right? At least in a game. Who knows how it happens in real life? I'm not a psychologist. So that's an issue. So if we imagine like a whole bunch of things we might want to have happen in games, sort of represented as verbs in this case, we could get things like shoot, patrol, farm, sleep, hide, hunt, etc. All of these things are more than one rule, right? If nothing else, they're a thing that has to happen, plus like an animation that needs to run, plus a sound effect that needs to go, and so on and so on and so on, right? So the easiest way to bundle all these things together conceptually is generally with what we call a state. So that's how we're going to end up talking about these things, as states that we are in and doing things in. Now, most game agents have to go through more than one state, right? So, you know, over time, depending on the context, game agents will be in different states. They might have different ways of moving through those states based on their purpose in the game. They have some shared states and some distinct states, depending on who and what they are. So for example, here, we could have like a guard, and the guard states might include patrolling, attacking, and hunting, right? And they do these different things based on different conditions. But we also might have just like a farmer, right? And that farmer or villager might also have patrol, like the guard, but also has distinct things other than the guard that they need to be doing. So some shared states, some non-shared states. And the distinction between them is really when do they transfer into these, right? Well, note for those of you who are more familiar with like reinforcement learning, this is a very different meaning than state in reinforcement learning, right? A state in reinforcement learning is a notion of context around you. This is a state of being. This is what you are in right now. This is how you are acting right now. So in terms of decision making, when it comes to using states, because finite state machines are used in like quote unquote standard AI as well outside of games. I should really just say non-game AI here because it's so broad. But basically, it's about making the optimal choice of action that maximizes the chance of achieving some goal. So finite state machines, the thing that we're going to be talking about today, are really, really simple and very fast. And that means that it's very handy for particular kinds of standard AI applications. Like if you have an Alexa or Google Home, it's basically running a finite state machine, in addition to more complex AI that's doing in each of those states. But that's sort of its goal. It's trying to achieve some optimal action. But in game AI, instead, we're just choosing the right state to support the experience, right? We just don't want to knock the player out of the experience. So our state here, our notion of a state here is some combination of animation and mechanical effect in the game engine. So we might have an attack, right? Where in an attack, we could have an animation where the player, is being attacked by this agent. The agent is swinging at the player. It could also move towards the player, check to see if the player is hit and does damage if so, right? This could be the entire attack state. I also included, you can find these for a whole bunch of in-game characters for variety. Oh, no, that's not. I guess I can't just click. That's fine. Don't worry, I'm not showing audio today. Audio is the real killer. Of course, I've already frozen because why could I have nice things, right? Let's do it like this. So you can find, bet there's gonna be an ad. Bet there's gonna be an ad. Yeah. No. Why is Vegeta here? All right, anyway. Yeah, 400 views on YouTube should be a good video. No, not gonna load, that's fine. Small screen you'll load. There we go, okay. So this is the large body enemy from Kingdom Hearts, Heartless. Has anybody seen this thing before? Okay, some hands, less than I would expect, but that's fine. I'm just very old now. This creature, right? Each of these animations that we're about to see represents a distinct state. So for example, here at the very start, we have this large body, which is sort of idly looking around, right? So this is an idle animation. It is an idle animation just going to play when nothing else is happening, but this represents a distinct state of being. There are no other checks happening, but we could potentially transition into doing other things. So for example, we could start ... walking towards the player, right? And then we could potentially be hit. Being hit is a distinct state, just like that. Oh, that's all I get, apparently. Lots of different hit states, you'll note, because there's lots of different attacks in the game. Each of these represents a distinct state. Also knocked down, getting back up, distinct state. Confused or dazed, distinct state, and so on and so forth. You can find these kind of animation reels for basically everything. The important thing to note here is that while obviously there's a distinct animation here, the animation by itself doesn't actually convey anything mechanically. Nothing is going to happen mechanically just because the character looks like they're dazed. Instead, we have to have code that supports that, right? And that combination of the code supporting that in the animation, that is what is the state, okay? Cool. Let's see what comments, funny comments people are making. I love Kingdom Hearts. Get ad blocker, LOL. It'd be a very funny thing if I, as a professor, was like, definitely everybody go get ad blocker. That feels very legal of me to be saying. Okay, so let's jump back here. So finite state machines, right? That's the thing that we're going to be talking about. Historically, there's a mathematical model of computation, which is just to say it's a way of representing distinct states of beings and the transitions between them. The way that we're going to be, it's also called like finite state automata. There's like lots of names for this. It's a general game AI model for agent behavior with these sort of parts. We have some finite number of states. That's important. We have some finite number of states. And again, these are the states that are the distinct states of being, an animation and a combination of rules, often represented with I. We then have a transition function, which basically tells us under what conditions do we go from state to state prime. Then, finally, we have 0 or more final states. So you don't necessarily have to have a final state, but for certain kinds of things you might want to. So for example, imagine like a homing missile that gets shot at something in a game. That homing missile is an AI agent, and it has a very simple finite state machine that has a distinct end state, right? Whenever it hits something, it's going to blow up, and that's its final state. But you might have other entities that don't have a final state in that way, okay? Okay, so here's a very common way of representing or visualizing finite state machines. So all of these nodes, big blue nodes, these are states. And the edges with the text on them, they represent the transitions, with the text being the condition on which we do that transition. So in this case, we have gather treasure. So this is some kind of adventure or final state machine. We're gathering treasure. If we see a monster in sight, we're going to flee from that monster. We have 2 transitions away from flee. So we can either see if there's no monster, we can go back to gathering treasure. And if cornered, then we're going to fight. If at any point the monster is dead, then we go back to gathering treasure, and that's it. A couple of things that are important to note here. One, if there is not a connection between the 2 things, we cannot jump between them. So there's no world where we can go directly from gathering treasure to fight. That's not possible. There's not an edge there, so it's not possible. In addition, we can only do the things represented by these states. So you'll note here, there's no state about dying. There's no state where we die to the monster. And so because of that, in this state, represent the character dying. Okay? You can also not just represent it as like nodes in a graph, you can also represent it as tables like this. This is pretty straightforward. So you say, hey, what's our current state? What's the condition on which we do the transfer? And what's the final state? This is an easier one to say right down for a quiz. Hint, 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 hint. So worth understanding what's happening there. Speaking of worth understanding what's happening there, PQ1. So what I want you to do here is to design a finite state machine for a security guard. I've even given you the states that patrols a school after hours. If it sees the player, it needs to seek the player and give them a lecture till the player can slip away. Otherwise, you should switch between idle and patrol. States are going to be idle, patrol, seek, and lecture. All I've asked you to do is basically fill out a table saying if you're at one of these states, what can you transition to, essentially. That's the nature of the PQ. And then feel free to make use of any variables or conditions you want. You can either just describe in text what it should be or just name it something that's obvious, like sees player or something like that. Okay? Cool. Take a few minutes to do that, and I will write it out in the Discord. People are already asking about homework 3. oops, that's not the right one. Okay. Just pause the share real quick. Yes. Go ahead and load up. Let's take a look at some of y'all's answers. Okay. Okay, we got some answers. Let's go ahead and talk about this. So let's as a reminder, let me bring both of these up side by side as best I can. So my instructions here were to use idle, patrol, seek, and lecture. And we were supposed to go from idle to patrol at random, basically. Or no conditions given to you, but basically at random. You should be patrolling a school after hours, right? If you see the player, you should seek the player and give them a lecture until the player can slip away. And I gave you 4 states. So if going from idle, most people are saying that from idle, we should go from patrol and seek, but people didn't give conditions. Giving conditions is very important here. Periodically to patrol, this is a reasonable one. Been idle for X seconds, as for going to patrol, I guess, but you have to give me, again, you have to give me the state that we're going to and the condition. So seek on seeing player is a reasonable answer. Patrol by itself is not. If we didn't have a condition on the transition, we would transition every single frame. So we have to have a condition on the transition, which is just a fun thing to say. Okay, going from patrol, again, same kinds of issues here. On player spotted, seek the player. This is a reasonable one, though said seek as the name of this condition, because that's the one that's given to you, or the name of the state. From seek, lecture, idle, patrol. I think some people were just listing all the other states they could think of, which is very funny. But you do have to be explicit. Designing it ahead of time is important. So let's since it's unclear, right, exactly what you needed here, let's go look through my answer. I think the share is still working. Yeah, okay. So here's my answer. Rather, it's an answer that I'm giving you for a very particular reason. And we'll get to that in a second. So I've given you the 4 states, which are represented as nodes here. Idle, patrol, lecture, and seek. Let's start with idle. So what I've basically said is we want to spend 5 seconds in each state, or rather, greater than 5 seconds. You want to transition from idle patrol or patrol to idle. That might seem kind of short, but if we're in a video game where like you're sort of like watching this guard maybe hidden from something, if they're like standing still for 1, 2, 3, 4, 5, and then they start walking again, that actually feels pretty reasonable. So that's why that's that. From patrol, I give an option here of seeing the player. So this is just a Boolean that I'm imagining exists. I've just invented this variable. So if I'm seeing the player, then I'm going to go to seek. And that's it from patrol. It's the only thing we get from patrol. From idle, you'll note, we can also see the player and get to seek as well. So we have those 2 transitions from idle and patrol. We can get to these 2 other states from there. Now seek has 2 transitions as well. We can either, if we don't see the player anymore, go back to idle, or if we are close enough to the player, then we can lecture the player. And if the player manages to sneak away from us, then we go back to idle again. Does this make sense? Does this setup make sense? And it makes a little more sense the kinds of answers that you would want to give me on a question like that, say on a quiz? Okay. Appreciate the nodding. Let me know, as always, if there's any questions on that. So some advantages for this. It's ubiquitous, right? So I mentioned before, this is used not just in digital games. Basic things that are essentially FSMs are used in a whole bunch of at-home sort of AI type devices and on things like Mars rovers. It's very quick and they're simple to code. I'll give you a few examples of how you can implement these in just a second. They're relatively easy to debug. So the nice thing here, the reason why there's an asterisk, is that you can always know you can only be in one state. On a particular frame, you can only be at one state at a time. So that means that it's really easy to track down where should you be looking. Imagine we have a FSM with like a dozen states. If we can say, oh, there was a bug that occurred and here's the state where it occurred in, we can cut down where we need to look to find the bug. It's just that simple. But the other problem here is that it can be kind of hard to track down a sequence of what was true in the world that led to it making these sequence of unintended state changes. They're fast because they have a small computational overhead, right? In terms of making a decision of what state we're in, at worst, in the worst case scenario, it's the number of edges from our current state. Does that make sense when I'm saying that? Because every state, we know we're, sorry, every frame we know we're in our state. We're in one state in that frame. We only need to check if we need to transition to all of the outgoing edges from this state. The only things we need to check. And otherwise, we just stay in this computation. So it's pretty fast. Now, the states can be themselves computationally complex. So if we're talking about your Alexas or your Amazon homes or things like that, right? They're running, fairly complicated server calls to deep neural network models hosted on servers somewhere. That's fairly expensive. But the individual state is figuring out what state you're in. That's cheap. They're also fairly intuitive, right? People already do this thing. They group behaviors together in this way. That's why if I was just showing you those animations, right, the majority of them read to you like, oh, I can understand mechanically what should be happening here. Because it just sort of fits. And finally, they're flexible. They can represent all kinds of different behaviors. No, not finally. It's also easier for designers without coding knowledge. This one's important. In industry, when we're actually talking about implementing games, most of the time, designers do not understand programming all that well. They typically can describe, hey, here's the thing I want, but they can't necessarily describe specifically like, here's the implementation I want you to do. So if they can describe things in a sort of intuitive way, like this, right, it's easier then to do the adaptation. But there are then, of course, some disadvantages that go with this. So when it fails really hard. This is the important thing I was trying to highlight earlier, right? So a transition from one state to another requires forethought. You have to think, we have to be able to go from this state to this other state. Let me show you an example that was just already here. So hold on, how do I get back to the screen? Okay, I can, here we go. So here's a case where we can lead to a really weird bugged behavior. What if we get into a scenario where we're in patrol or we're in idle, right? And we end up close to the player. What we have to do is we have to first get into this sort of seek behavior, and then we can start lecturing. But we have to have like a weird jitter frame where for a second we start like running at the player before we stop and start lecturing them. Does that make sense? Because you can only be in one state at a time, and you typically either transition at the end of a frame or at the beginning of the frame. That means we spend one frame in seek. So for one frame, we'll be running at the player before we start lecturing them, which is weird, right? Now, if I thought about this ahead of time, and of course I did think about this ahead of time of doing this for the example, but if I had thought about this again ahead of time in this hypothetical situation, I could have put a connection here from idle and patrol to lecture directly. But I would have to have thought about that ahead of time. So pretty significant disadvantage. Let's look at a quick example. We're doing okay on time. So this is again, thankfully, I'm not going to try to do audio again in this setup, I think. Fingers crossed we get another terrifying ad. Oh, thank goodness. Raid Shadow Legends. All right. So this is behavior that you all are going to be very familiar with. See that Goomba up there? Caught on this edge. Does that remind anybody of anything? Maybe in one of the assignments you've seen? So already you've been basically working with an FSM. It's just one that wasn't explicit, right? Your Pac-Man, which could be idle or it could be moving somewhere. And you could run into a situation where it should be moving back to idle, but it keeps on getting stuck on something. It does this weird sort of thing happening here. That's the exact same thing happening here. The Goomba, right, which is an enemy, if it's close enough to Mario, should be moving into an attack position. But because it's caught on this edge, it can't transition away from the movement state. All right, jump back to here, do this one. Okay. So other than this issue, we also have this problem that the number of states can grow really fast. It's exponential with the number of events in the world, right? Because we can have multiple ways of reacting to the same event given different variables. So we can have to author in lots and lots of states if we want really, really complex behavior. Now, there's ways around this. We talked about this already, right? That in The Sims, for example, we've moved the sort of logic of what states you're in with the animations and mechanical benefits into the objects that the Sims interact with, rather than having to have it in one giant FSM. It's more like it's more distributed of an FSM. So we don't have to worry about when there's objects in the range. But generally, right, if we want to have a very complex AI, we have to have a lot of states, and that gets very complex. The number of transitions, right, can grow even faster than the number of states, because I just showed you an example where, in fact, we basically wanted a way of transitioning from every state to every other state. And then at some point, we've cut down the usefulness of an FSM because we have to check every single state every single time we want to do anything. So not ideal. Finally, and this one's really killer, it doesn't work with sequences of actions or memory. So all we know is the state that we're in, right? Maybe we can track the state that we were just in. But if we wanted to have notions of sequences of states over time, there's no way to do that with a standard FSM. Okay, so a quick sort of example here, unsurprisingly, is Pac-Man. Wow, who would have guessed? Weird, right? So we have here Blinky, Pinky, Inky, and Clyde, or if you like, Shadow, Speedy, Bashful, and Pokey. These are the 4 ghosts that are in the original Pac-Man. Has anybody played the original Pac-Man? Probably at least some of you, yeah? Cool. So if you're not familiar, this is something that's going to be very relevant to assignment 3. Each of these ghosts has distinct behavior. So one of the earliest games where each of the enemy AIs had distinct sort of quote unquote personalities. And each one of them is based on a very simple FSM. So the way this works is that each of them has their sort of distinct state, which is unique to them. Then when they sort of are see Pac-Man eating this power pellet here, they all transition to this like threatened ghost state. So that's a shared state between all of them, where they basically act at random and they sort of wander around the map and they can be eaten by Pac-Man. Finally, and this one is not obvious to people who've played Pac-Man unless you're like super into Pac-Man for some reason, which I don't know why you'd be. Each of these has a timer in their default state, at which point they go to what's called a scatter state and they go to one of the 4 corners of the map. So those are 3 simple states. Oh, there's another one, which is if they get eaten, they turn into eyes and they run back here. So technically 4 states. So all of these is a very simple 4-state FSM. And you're going to be implementing 2 of them for assignment 3, plus an extra one. Okay, so in terms of implementation, there's a few options. A very standard one is to basically throw everything into a massive switch statement. Are people familiar with switch statements? Yeah, okay, yeah. So it's basically just a complicated if-else, essentially. It's simple, but it's nice and extendable, right? So we could just have some notion of, hey, what state are we in, represented as an integer, an enum, or whatever, some kind of object of some specific type, discrete types. Then we can have particular states represented like this. Pretty easy. But the problem is then you have all of your code in one massive file, which is generally not ideal in terms of like debugging and code cleanliness and stuff like that. So an alternative to this would be, why did it do that? Having a state as a class. So this is the representation that we'll be using for assignment 3, where every state is going to be represented as a distinct class, a distinct script. This is a little bit nicer because basically it's extendable in a way that doesn't create massive amounts of code in like one single area. We can also then, reuse the same script, the same state, the same class for multiple different entities, which is something that we can only do here by like copy and pasting code, which generally you're not supposed to do, but I don't really care. But in this case, it is the better option. And then, an agent is just going to carry a reference to its current state. Why is it? Ooh, I'm kind of mapping back and forth. That's fun. Then finally, why does it keep on restarting? This is very strange. Then finally, there's the state is like a lookup table. So you could just have similarly representing your state code wherever it is, but then you just basically have a defined lookup table, often literally represented as like an Excel table that then is accessible to designers. We're not doing that. Right, so state as class typically looks something like this, right? We have some interface called entity. We have update, right, where thinking happens, quote unquote. This is where all the game logic happens for this particular entity, right? This is the Unity setup. And then we have some notion of like change state for this entity, because the entity is going to store a reference to their state. Separately, we could have an interface state, which could then be implemented in a number of different distinct states, right? Number of unique states, which has the following bits. Execute, this is the thing that happens when you're in this state, right? On enter, this is what happens when you first enter the state. And then on exit, which is what happens when you're leaving the state. This is exactly the setup, though I didn't make this. I stole this from another game AI lecture, but this is the exact setup that we're using for the Pac-Man for assignment 3. Any questions on this? Does this sort of make sense? Cool. Second PQ. PQ2. Question. How can we avoid getting stuck in a state? The naive thing would just be to think ahead and to design all possible transitions that might be needed between states. But this is the designer solution. And also it's a very slow solution. But this is an AI class, technically. And so really we should be thinking about what alternative representations with alternative AI approaches could be using that are going to cost less design effort. Make the AI do the work, not the human. This. Oh, sorry. I'll turn it back on in just a second. I just want to open up the question on my side. Just like that. Oh, wow, y'all are a lot faster with this one. There were fewer questions, though. Okay, so let's take a look here. We have some people suggesting we could add an extra state where you go to the state if you're stuck for more than 5 seconds. This is an interesting idea. So this is still a sort of designy solution, right? Because this single state basically now acts as a hub. And it means that we have to basically check every single state when we go here. So it sounds pretty computationally expensive to me. But it's a reasonable solution that could work. The only other problem with it is that you are going to have your agent pause for a second, right, with their behavior every single time you go to this like hub state, which might not look right in some particular kinds of games. If stuck in a state for longer than usual, just reset back to a default. Same idea. Have a default state. Yo, really like a default state. Dang. Default. My goodness, what is going on? Y'all really like that. Have a set timer for each state, default state, keep track of how long the entity is in a state, add forced transition read since it's stuck. Again, that's just thinking ahead. Break the state, no. Wow, y'all just really like defaults. Dang. What is going on? Okay, I mean, it's not a terrible plan, but it is one that I think we can do a little bit better than, again, because of the reasons I outlined around pausing and around doing a lot of weird transitions where we just have to do a whole bunch of checks. So I'm going to talk about 2 extensions here for about a few more minutes, and then we're going to transition into talking about assignment 3. So we have 2 sort of main ways of trying to extend FSMs. One of them is called a stack FSM. So the difference here is that rather than using like a lookup table, like a dictionary or something like that to track your states, or even to set classes to track your states, instead we're going to use a stack representation to track our states. So what we can do is we want to push a new state onto our stack. Instead of having an agent just store, hey, here's my current state, we're going to have a stack of states that we're telling it, hey, do these things. And then when you're done with that, we want to pop that state off and we go back to whatever that sort of last state was. So a stack, if you're not familiar, because again, this is in a data structures class, that just means that whenever we add on to it, it's put on top, right, like a stack. So it means we're always going to be doing the last thing we were told to do. And then if we need to go back to doing something else, we just pop it and we do the last thing. Simple. We can also do the same thing around being stuck. If we're stuck in this top state for a very, very long time, it's not completable, then we'll just go ahead and we'll jump down to the last one. Easy. This mostly works, but sometimes it can lead to weird stuff as well, right? Because we can end up going back to a state that doesn't actually make sense contextually. But this is kind of similar to, this isn't how it works. This is kind of similar if you remember like the Skyrim stealth example that I gave you a bit ago, where the characters sort of went back to going like, oh, I guess there's nothing there, and like sitting back down on the table, right? So it can feel unnatural if you're just sort of like going back to an idle when it really doesn't make sense to. You can also have a hierarchical FSM. So the idea here, it doesn't get rid of the design effort, but it does at least allow you to feel more gracefully. The basic idea is that you have 2 or more FSM levels, And the basic idea is that we have an abstract FSM that moves us between the sort of lower level FSM states. So you sort of have two layers of an FSM. And what that means is if at some point we're stuck in one of these abstract states, we can go to a different abstract state. So let me give you a couple examples here. So in terms of stack FSMs, right? Let's imagine this example earlier. If we've gotten into the situation where we were close enough to see that's not going to work. Let me do a different example here. Let's say that we're in a scenario where we got into lecture, right? But even though we got into lecture, the player is like just far enough away from us that we can't lecture them, but we can also still see them. So just to be clear, what's happening here? We've gotten into lecture, the player was close enough right in front of us. The player is now getting away from us, but we can still see them. So we're now trapped in lecture, right? Now with a stack FSM, if we were in lecture for a long time, we could go back to our previous state, which would have been the seek state, right? So that works out very nicely to us. That's beneficial. But the other version, the earlier example that I give you of saying like, what if we're in idle or patrol and then we get close enough and we see the player, that doesn't help us at all. We still have to do this double layer of transitioning, okay? But it does help for the very particular scenario of the player sort of slowly sinking away from you, but still in view. Here's an example of a hierarchical FSM. So all the colored sort of boxes here represent one of these higher level FSMs. So we have die, idle, etc. This is about a dog. So just don't look at this corner if you don't want to think about this corner. There's just a dog entity. It's not a real dog. No real dogs were harmed with this. Also, anyway, are distinct states that the dog can be in within that. And there's even some times that are shared between these things. This creates a whole bunch of extra complexity, but it does mean that if we get stuck anywhere in here, like look at how complicated this attack FSM is, right? If we could get stuck in any one of these states, if instead of saying, oh, we have to figure out a way of transitioning away from this, we could instead figure out a way of transitioning to one of these higher level things, like going back into idle. Does that make sense? But again, it takes a lot more authoring to be able to do something like this. Unlike usual, I'm going to do a whole bunch of references here because FSMs have been written about a heck of a lot in terms of in and around game AI. This is just if you're interested, you can check these things out. Okay, so with stacked FSMs and hierarchical FSMs, we've gotten rid of some of the disadvantages. It's harder to get stuck in a state, and the number of transitions can greatly. Talk about having hierarchical transitions, or if we can talk about having the ability to just jump back to the previous state. That's a benefit. But what if we want to do things like, say, failing gracefully, right? Where if we get confused, we can sort of enter more and more general states until we find something that works. Or let's say that we want to encode a sequence of states, right? Sequences of actions over time, without having to bog each state down by, say, tracking additional variables or conditions, which would be the other way that you could do it. So what if I told you that there was this approach, configure trees, that were popular in the industry since 2004, easy design, easy to alter, fail gracefully, all near you, aka on Wednesday. So behavior trees really are the AAAI game AI method of choice in terms of doing decision making. And that's what we're going to be covering on Wednesday. The reason why Halo is here will become clear when we talk through it on Wednesday. Okay, next is the assignment 3 review, but are there any questions on FSMs? Again, as a reminder, this is one of the topics that will be on your quiz on Friday. No questions? Okay, everybody's an FSM expert? Phenomenal. Okay, well, I don't have to worry about that. I guess you're all gonna get, full marks on every single FSM question. I look forward to not thinking about that critically. Okay, so let's do this. I'm going to go ahead and load up that. And while I'm doing that, let's go ahead and here we go. Great. Okay. So, oh, hello. So as per the usual, I'm not going to read this whole thing out to you, but again, I would recommend actually reading it. There's a whole bunch of hints that I put in every single assignment, and then people ask me questions that directly relate to those things I've already said in the assignment. where they say, hey, can I do this? And the assignment says, no, you cannot. So please read the assignment. I know I say that, and the people who are always going to read it are going to read it, and the people who aren't going to read it still aren't going to read it, but I'm saying it anyway. So you'll note this is what your assignment's going to look like. It looks a lot more complex than previous assignments. It looks more like actual Pac-Man. It's because as we're going, you're going to get more and more to like a real Pac-Man game here. Then you'll go beyond it for the final assignment. So your basic goal here is to implement the FSMs for each of the ghosts, as I mentioned earlier. So there's a few things that you're going to need to know. You are going to have to implement 2 ghosts, Clyde and Pinky. Talk about those in a sec. And you're going to have to make your own custom ghost. This is a ghost that is distinct to you, that was not in the original game. For these, all of these scripts inherit from FSM agent.cs. You're barely going to have to change these 2 scripts because all the intelligence in an FSM is in the states, right? So primarily, you're going to have to be creating new state.cs or new states that inherit from state.cs. Okay. The basic state function works exactly as I sort of described earlier. There's an update function that says, what do you do in the state? There's an enter state that says what happens when you enter the state. And unsurprisingly, there's also an exit state that happens when you exit the state. There's also an FSM agent. This is the primarily thing that you're going to be interacting with in terms of getting variables and things like that. So there's a whole bunch of ways of getting information here. There's also some secondary things that I outlined here at the end. These are extra sort of singleton interfaces that you can use for grabbing specific kinds of information that might be helpful depending on what you're imagining for your custom ghost. Okay. Not going to cover those in detail. Okay, so let's go ahead and jump into this. Basically, it's this very simple game where the goal for the Pac-Man is to eat all of the 208 pellets that are in scene 1. But the game will not end when that happens. You're going to have to restart it. The game will restart automatically whenever the ghosts eat Pac-Man. You're not going to be graded with the click control Pac-Man. So let me just go ahead and jump in and show you what's up here. Okay. So if I hit play here, you're going to know here there's Pac-Man, there's some power pellets, comes a ghost. So the ghost is going to rocket towards me. I can click to go to a particular location. I went too slow. Oh, this is going to be really slow as well with the frame rate. Ooh, okay. You can do it, Pac-Man. You can do it. Ah! Okay, there we go. So now he's gotten eaten by, oh, there we go. I can eat him. He turns into eyes. You get some weird behavior happening there. I'm using a very bad pather. This is the default pather that you're given, which you can use for the whole assignment, but you can also replace with your own A-star Pathfinder. Oh, those eyes are trying to get home. Oh, they're trying to get home. There we go. And then I can get eaten and restart. So that's the basic setup. So that is with Blinky. There are 2 ghosts that are given to you. Blinky and, is it Clyde? No, Inky. Blinky and Inky. Oh, hello. Hello, Unity. Fingers crossed it doesn't crash, but I'm betting it's going to crash. Yes? Let's try clicking away and clicking back. Ooh, no, 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 no. Didn't like that. All right, let's try that again. Okay, so that was the basic thing that I just showed you, right? Going out and hitting play. You can replace the grid handler, but that's not so important. You can also replace the A-star Pathfinder. That's a little more complicated, but it will lead to slightly better performing code. Let's see. Let's go ahead and show you. So that was with Blinky. So we can also go here to admin, and there's a few interesting things happening here on admin. One of them is this ghost manager you'll see right here. So I can also go ahead and throw in Inky right here instead of Blinky. Ooh, my laptop sounds like it's about to explode. Very exciting. And if I do that and I hit play, wait a few seconds, and instead Inky spawns. This behavior is not unusual. This behavior is not unexpected. In the actual game, Pac-Man can't sit still. So if you're only testing with your mouse click agent, you're going to get weird behavior like this. So what you instead want to do is use a different agent. So you'll note here that it says mouse click agent, but you'll note over here there's a whole bunch of different Pac-Man agents. Arrow key agent, greedy coward, mouse click, and random. I'm going to go ahead and replace mouse click, delete that one, and then go to random and just throw random onto the screen or into the hierarchy, hit play, and then no hands. Here's random. This is just doing it purely at random, right? So just doing random interfaces at any point. Kind of looks like it's chasing it there. Very good. You can get in this fun situation, but eventually it will resolve itself. It's fun to just watch them go. Let's look at a slightly more intelligent agent. So rather than purely at random, we can also have this greedy agent. Greedy is just going to go for the closest pellet at any point. Does actually a pretty good job. It will eventually die, especially if he's going up a blinky. But there is a little bit of randomness. It's mostly deterministic. So your job is not the Pac-Man. The Pac-Man are given to you. Your job is the ghosts. So let's talk about that real quick for the last few minutes. As per the usual, the homework assignment is worth 10 points. Your solution will be, again, created by an autograder as always. I'll note this is the first time where your code should be significantly different from any other code I'm seeing. So be careful, basically. Don't share code. So you can get 2 points for a correct implementation of the Pinky Ghost. As always, this is not all or nothing, except for the very first one with the grid assignment because it sort of has to be. But for the Pinky Ghost, it's not all or nothing. There's parts of this Pinky Ghost implementation. We'll get different points for different parts. Then 2 points for the Clyde Ghost. That's the orange ghost behavior described in just a second, or actually just above this. 1 point for the custom ghost. So this is your distinct new ghost, whatever you come up with. You have to have 3 new states. So this means 3 entirely new states, not making use of the existing states. So that means that you're going at minimum 2 states beyond the sort of complexity of the original ghosts. Okay. I go into the detail here. Basically, the behaviors can't be the same between any of the existing states. By behaviors, I really mean the position that each the ghost is in from frame to frame, and the transitions between those frames. That's how I'm tracking the similarity of behavior. Then your final 5 points. That's right, 5 whole points. Half of the score here is just on that your custom ghost is going to more quickly eat the 3 given AI Pac-Man agents, which is random, greedy, and greedy coward, and 2 withheld agents you're not going to get to see. So withheld agent 1 with agent 2, which are better, right, as you would expect. Notably, you cannot access the custom ghost game object or transform in your code because then you can just teleport the ghost directly to Pac-Man. If you try to do this, the autograder will fail and you'll get a 0. In addition, we have the extra credit, right, which I should also briefly talk about. So it's easy enough to make a really overwhelming agent, an agent that just always beats the enemy as quickly as possible. That's simple, right? This is actually the hard thing when it comes to game AI. It's not making an overwhelming enemy. That's just too difficult. It's no fun. So instead, you have to make an agent for the extra credit that fits the game design of Pac-Man. What I mean by that comes in 2 parts. First, in addition to the 3 new states, your ghost must make use of the original states, scattered, frightened, and eyes at the appropriate times. This means that by default, if you just want the 10 points, you don't have to make use of these states, which will also already give you a massive leg up over the competition. Then, if the other thing that you need to do is that your ghost must be harder to deal with for simpler AI agents and easier to deal with for more complex AI agents, aka it represents reasonable, difficulty for these different agents. It has a difficulty curve to it. So essentially what we'll be doing is we'll be tracking how it does against the 5 agents. And it should look like this, right? Where the random score is less than the greedy score. This is the number of pellets that you can see at the top right corner. Then the greedy or coward score roughly equal to or less than the withheld agent 1 score, less than the withheld agent's 2 score. Cool. Any questions high level on this? There's some hints here at the bottom. The last thing I want to do while I have a couple minutes is talk about this. So what I meant by correctly implementing Pinky and Clyde is right here. So to do that, right, both ghosts should follow the correct things in the game in terms of when to go to their scatter and frightened states. You can see examples here for Blinky and Inky in terms of when to go to those states and how to use that code. You can replicate that code, I don't care. But obviously it has to be in its own distinct new state. Both ghosts should also go to the correct corner of their map when they scatter. You can find the correct corner of their maps right here, right? Pinky's is the top left and Clyde's is the bottom left. Pinky should target the grid cell closest to 4 grid cells in front of Pac-Man, given Pac-Man's current orientation, and Clyde should target Pac-Man until he is within 8 cells of Pac-Man, at which point he should target his scatter position. Okay? There's more details here. This goes actually an extremely deep dive into the AI of Pac-Man. You do not need to implement all of this. Every year I have students who are like, oh, but we didn't do this weird corner case. What about that? Like, don't worry about it. This is what you need to do. But if you want more details, do it. Okay. All right. Any last minute questions? Okay. In that case, I'll hang out for a few minutes after class as per usual. Feel free to let me know. Remember that you have a quiz Friday. Remember you have assignment 2 due tonight.
I have a question for the quiz.
Sure.
So, right now, for the original one is like or this one.
Okay, can you just email me about this? It's probably easier to look at.
Okay, I'll email.
Okay, sounds good.